Hey guys, welcome to 3.8 lesson. We're going to go over periodic trends. So I want to start here with looking at some of the models from the POGILs that we had yesterday. So here's model 1. If you have your POGIL, you might want to pull it out right now. And I just want to look at some of the stuff that we noticed. So in model 1, if you noticed that as we got further apart in distance, that our force of attraction here became weaker. Okay, so as an electron is further away from the nucleus, notice that it gets weaker. That will be really important today. And so if we're closer, right, then we are stronger. Okay. The second thing that I wanted you to look at was this. And it's really modeling the same thing. Notice that lithium has 2 shells, but it's also got a stronger force of attraction. If you notice how big that arrow is, that's signifying to you that it's got a stronger force of attraction. But as we go down a column, notice lithium and then underneath sodium and then underneath potassium, that our force of attraction gets weaker as we add more shells. Okay, so we notice that as my electron gets further away from the nucleus, it's weaker, but also as we add more shells, it's weaker. Okay. Here's our catalyst. For rhodium, write the unabbreviated electron configuration, noble gas configuration, and draw an orbital diagram. So I'll give you a moment to do that. So go ahead and hit pause, and then when you're ready, you can check your answers on the next page. Okay, so on the top here we have our full electron configuration. Down below, sort of sloppily written, is our abbreviated electron configuration. And then below, I've put all of the boxes that you would need to do your orbital notation. Now, please keep in mind that they must be labeled. So this needs to say 1s and 2s, etc. And so all of these will be filled until you get to the very end here. This is your 4D. And with 7 electrons, remember, you go in unpaired first. So 1, 2, 3, 4, 5. And then you go back and pair. 6, 7. So all of these boxes will be filled, and then this is what your 4D orbital will look like. Okay, now let's start talking about periodic trends. This helps a lot if you are looking at your POGIL while we're sort of talking about our periodic trends, because everything is coming back to that Coulombic attraction that you looked at in your POGIL yesterday. Okay, so periodic law. So the first thing is this: atoms with similar properties appear in groups or families on the periodic table. So as you go down a column, you should have similar properties. They're similar because they have the same number of valence electrons. So lithium is going to behave in much the same way that sodium is going to behave, in much the same way that potassium is going to behave, all because they have 1 valence electron. Okay, and that sort of governs their behavior. Okay, important terms to know, the first of which is called electrostatic or Coulombic attraction. And it's basically this: opposites attract, positive and negative, right? And so we looked at this here. This is from one of our models, right? We're looking at the attraction between my proton and my electron, right? That's that electrostatic attraction. So nuclear charge is the number of protons in the nucleus, right? The positive charge within the nucleus. So here my nuclear charge is 1. Here my nuclear charge is 4. Right? As my atomic number increases, then my nuclear charge increases. So these are 2 really fancy words that just mean opposites attract and number of protons. But I don't want you to get bogged down in the language. Okay. So valence electrons. Do you recall how to tell the number of valence electrons for the S and the P block? Okay, you just have to count across, right? So 1, 2, and then we skip the D block, and then we count 3, 4, 5, 6, 7, and 8. Okay. So general reactivity metals increase in reactivity down and to the left. So the most reactive metal, which is in the lower left-hand corner, is francium. Non-metals increase in reactivity up and to the right. The exception is the noble gases. So if you exclude the noble gases, your most reactive nonmetal is fluorine. Okay. Why are metals reactive? Metals lose electrons when they react. So group 1 metals are the most eager to give up their 1 valence electron. And the reason why is because they're 1 electron away from being a noble gas. Now, this is a really important part. The bigger the atom, the further the electrons are from the nucleus, which makes them easier to remove. Right? There's less electrostatic attraction if you're on a shell that's really, really, really far away. So francium has 1 electron in the 7th shell, which makes it a very, very, very easy electron to remove. That's why francium within group 1 is the most reactive of all the metals. Nonmetal reactivity works just the opposite. Nonmetals want to gain electrons when they react. So the halogens are the most eager to gain. That makes them the most reactive nonmetals. Most reactive nonmetals. But beyond that, the smaller the atom, the greater what's called the effective nuclear charge, right? And basically what that means is the smaller the atom, the more it wants an electron. Right? When you're big, you can sort of deal with the fact that you're missing that 1 electron, but when you're small, like fluorine, that 1 missing valence electron actually becomes much more noticeable, right? And you're closer to the nucleus, having only 2 shells, so the pull on a nearby electron is much stronger. So periodic trends. For each trend, it is important that you know the definition, the trend direction, and the reason why that trend occurs. Okay, we're going to start here with atomic radius. So atomic radius is, in the simplest definition, how large the atom is. And here's the trend. Radius decreases as you go across a period. The reason why is because as you add electrons, for instance, going from lithium to neon, right, you're adding electrons to the same shell. So you're increasing the number of protons pulling on that particular shell, in this case the 2nd shell, which is going to shrink that electron cloud, right? That's my 2s and my 2p. Right? I'm pulling those clouds in closer because they're still within that same that same energy level, the 2nd energy level. It increases as you go down a group because for every row on the periodic table, you're adding another shell or another energy level. So sodium is going to be bigger than lithium because you're adding another shell to the outside of your nucleus. So here's your reasons. So as you go down, you have more energy levels, and as you go to the left, right, you have a smaller nuclear charge or less attraction for the electrons, which means if you're going to the left, you're going to be bigger, but if you're going to the right, you're going to be smaller. Right, so now you're dealing with the nucleus versus your electron cloud. So here's a picture here, and like I said, so even though lithium weighs less than neon, right, neon is going to be smaller because it has 10 electrons it has 8 electrons in that outer cloud, but 10 electrons in the nucleus pulling in on that particular shell. On your periodic table, what I want you to do is this. I want you to circle francium, and I want you to write AR, right? Just for you to signify that francium has the largest atomic radius. So, check yourself. Which of the following has the largest atomic radius, and how do you know? Talk to a neighbor and see if they know. Same here. Which of the following has the smallest atomic radius? How do you know? Check with a neighbor. Our second trend is ionization energy, which is the energy required to remove an electron from an atom. If you think through this, it should be pretty simple to you that it's going to be the opposite of size. The smaller your atom is, the harder it is to remove an electron, right? Because if an electron cloud is small, that means that nucleus is really trying to hold on to those outer electrons. So you tend to increase from left to right across a period. As your nuclear charge increases, you are pulling that shell in closer, making that electron harder to remove. But it decreases down a group. That's because as you add shells, those outer electrons are further away from the nucleus and easier to remove. Okay, so if you go up, there are fewer energy levels, so electrons are very attracted to the nucleus. If you go to the right, nonmetals want to fill valence shells, not empty it, so it's going to be very hard to remove those outer electrons. So your ionization energy is the highest at helium. So at helium, I want you to circle it, and I want you to write IE. So check yourself and check with a neighbor. Which of the following atoms has the highest ionization energy, and how do you know? Same thing here, sulfur or chlorine. How do you know? Check with a neighbor. Our last definition is electronegativity, and it's the measure of an ability to attract electron. So how greedy are you for electrons? It increases across a period. Okay, so we know that as we move from left to right, we're trying to fill our valence shell. And that attraction for electrons is stronger as we get closer to a full shell towards the right-hand side of our periodic table. Electronegativity decreases down a group or sometimes remains the same. Again, because as radius increases, the nucleus is further away from those outer shells, making it harder to attract those electrons. So here's a periodic table of electronegativities. We're going to use this a bunch later, so you don't need to memorize this or anything like that. I do want you to note that fluorine is the highest. What do I not see on my periodic table here? A big group way over here. My noble gases, right? My noble gases are not on my electronegativity chart because they have no need to attract electrons because their shell is already full. So on your periodic table, I want you to go ahead and circle fluorine, and I want you to put En, right? So that you know that electronegativity is highest at fluorine. So that's sort of our summary there. In how atomic radius, ionization energy, and electronegativity sort of trend. If you circle those three elements, that's the easiest way to do it. Or if you just remember, like, francium is fat, right? It's the fattest element on the periodic table. And if you try and reason everything from that, it should be pretty simple. So, check yourself which element has the greatest electronegativity and explain. Here we go. Greatest electronegativity, explain. Okay, we're going to pause here and I'm going to start a second video.